Let us now talk about equilibrium between two systems in thermal contact. Okay, now let's first consider two systems. Let's say system A, another uh, system B. Okay, and let's say both of them are in thermal contact. Okay, so basically both of them are in. Okay, so there is an exchange of energy in between these two system. So let's say this A, this is B, and then this is diathermic wall. So there is an exchange of energy to reach equilibrium between these two system. And system A has got, let's say, volume VA and number of particles to be Na. Okay, and energy, let's say, EA, and this has got, okay, the system B similarly has got volume V, B, and B, number of particles, and then energy EB. Okay, now the total energy of the entire system, there is, when I call it now system, there is A plus B, the total system of the energy, which is, let's say, E. Okay, and so this will be equal to EA plus EB, the total energy of the system. So now the probability of system A possessing energy EA is, as we discussed earlier, this will be it will be decided by number of microstates at that energy. So let's write it like probability of system A occupying or possessing energy EA is equal to some constant C1, and let's say W1 E, function of EA. Okay, so this is given by this particular formula, and this is, so the probability of system A occupying or having an energy EA will be decided by number of microstate at that particular energy. Okay, similarly for system B we can have the probability of system possessing EB will be equal to, let's say, some another constant C2, and then W2, let's say this is EB. Now when these two systems are in thermal contact, there is an exchange of energy in between them, and then try to reach a common state. Okay, so what do we need to do here now? So basically I have to combine these two systems and find out the most probable state which will occupy an equilibrium state. Okay, so that means I have to apply principle of the joint probability, meaning the probability that the system, let's say the energy EA and EB are the two energy occupied by the system A and B in equilibrium. Okay, so the probability of system A possessing energy EA and then EB for the system B, which will be given by the product of two individual probabilities. Okay, so let me just write C1, so W1. Okay, so this is then C2 W2. Okay, function of EB, or I can write it like C1 C2 W1 function of EA. Then let me just shift a little bit this side, this particular expression. Okay, and this is W2 EB. Okay, so now since this W1 W2, these are number of, this gives you thermodynamic probability of the systems, it's a typically huge number. So the application of natural, or the taking natural log on both sides will be helpful mathematically to analyze. So, and here what in equilibrium will be that state where, as I said, it will take the most probable state, or the higher or the highest probability state. Okay, so that's what you have to do here in this expression. What you have to do, that we have to maximize the probability expression. Okay, so how do we achieve that? So before doing that, let us take natural log on both sides of the expression. So ln P will be EA EB equal to, then the other side will get ln C1 C2, which is constant. Then we get ln W1 EA, then ln W2 EB. Okay, so now let us maximize this expression and then equate it to 0, because thermodynamic equilibrium will be that state where which has got the maximum probability. Okay, so then let us maximize this expression with respect to energy EA, let's say. So so what I will do here, that derivative, I'll take a first derivative of this expression, okay, ln by EB, sorry, EA, and then equate it to 0. So what I will get here, okay, so in the right hand side I see that this C1 C2 is a constant, so I will get a 0. Okay, so the del P by del EA I'll get 0. Okay, then I will get del ln W1, so I'll just simply write W1 del EA, and here I can apply chain rule. Okay, so del ln W by ln EB multiplied by, so I use just chain rule here, ln EA. Now from this expression here, whatever we have written in on top here, I can see that since this total energy is constant, so I will get an expression from there. Okay, let me just write it this side. So I will get an expression in that case, that if I differentiate this expression EB by the A, we will get a -1. Okay. So if I substitute this value for this particular thing, expression, so then I will obtain, okay, so this will be ln W1, okay, EA minus EB. Okay, so now this expression I have to equate it to 0 as I have done here. So then what I will get there, so this is 0, so in that case I will get it ln del ln W1, let's just put back this E, del EA will be equal to del ln W2 EB. Okay, so when these two systems reach thermodynamic equilibrium, then we see that these particular expressions are, or these functions are equal for the both, meaning either side of the system we see that this particular function is equal to the same function for the other system. So we can say that whenever two systems reach thermal equilibrium through this thermal contact, we can see that the function del ln W by del E, this is constant. Okay, see, from thermodynamics point of view, so this is from the statistical point of view. Okay, so from thermodynamical point of view, we know that the two system reaches thermodynamic equilibrium whenever there is a temperature of the both the system is same. Okay, or which we can say that the temperature is constant for both the system. Similarly, from the statistical point of view, I can say that this particular expression is constant for both the system, and I call this a beta. So I write this the beta parameter. Okay, so this is beta parameter. So this expression is typically called as beta parameter. So if I write for the system A, this is beta 1, let's say, and this I call it beta 2. So in thermal equilibrium or in equilibrium state for this system A and B, if they are both of them are in thermal equilibrium, then I say that beta 1 is equal to beta 2. So there has to be some relation between this statistical or the equilibrium that we are trying to discuss from the statistical point of view and the thermodynamics point of view. Okay, so there has to be, it's the same two systems, so just approach is different. So one is from the statistical point of view and another is from the thermodynamic point of view. So then there has to be some kind of relationship between this beta and temperature. Okay, and temperature. So if you see here, this W is a number, so so this dimensionality of this is nothing, and other side it is energy. So beta has got dimension of inverse energy. Okay, so therefore this beta is taken as, in fact the 1 by beta is taken as, so this 1 by beta is somehow related to temperature. Okay, and this beta, sorry, when I'm writing, okay, so 1 by beta is taken to be some constant k, okay, then t. Okay, so 1 by beta is kt. This k is proportionally constant, and it will be decided by the scale we choose to depict or use to measure the temperature. Okay, and if we use the absolute temperature scale, then this k is Boltzmann constant. Okay, so here we obtain expression or somewhat a relationship between beta and kt, where beta is a parameter which remains constant in thermodynamic equilibrium for systems. Okay, if two systems are in thermal equilibrium, then it's from the statistical point of view we say that the beta parameter for both the system is constant. From the thermodynamics point of view, we say that the temperature is constant. Okay, now here is a point. Okay, so see, from the statistical point of view, when we talk about equilibrium state of the system is that state which has got maximum probability. Okay, so from the thermodynamics point of view, you typically think about whenever there is a spontaneous process. Okay, so system is trying, let's say spontaneous expansion of gas, okay, diffusion of gas, let's say. Okay, so in that system, what is happening? So system is trying to move naturally from the less probable state to the more probable state. In due course of this the process, what is happening? The entropy of the system is increasing. So in thermodynamic point of view, the equilibrium of state is that state where the entropy is maximum. Whereas from the statistical point of view, the thermodynamic equilibrium, the equilibrium state is that state where the probability is maximum. Okay, so the thermodynamic probability or the probability of that state is maximum. So there has to be some kind of connection between these two things, because we are talking about the same equilibrium state of the system. Okay, so that's why the Boltzmann gave idea some kind of there has to be a relationship between this thermodynamic probability or the most probable state from the statistical point of view and from the entropy. So this we will see in the next slide or next video.